So what do all these interesting oxidizing agents do? So let's start with an epoxidation. So if I treat an alkene with MCPBA, the metachloroperoxybenzoic acid, what happens is it transfers one of the oxygens from the peroxy acid to the alkene and gives an epoxide. Now exactly how does that work? Well, this is a little bit complex, but I'll draw it for you. And I'll just draw a generic peroxy acid. Of course, you always have to ask who has electrons and who wants them, and who has electrons, it's an alkene, so that's always going to be the alkene. So the alkene electrons are going to come out. Now they're actually going to come out to an oxygen. So this is a little bit strange, but it has to do with this peroxy bond, that oxygen-oxygen bond, in the same way that it could come out and attack one side of a halogen. Well, this lone pair from the oxygen will come back here, and that's going to form the epoxide bond. However, at the same time that this happens, electron pair from the carbonyl will come out and grab that proton. So now this pair of electrons is free to go somewhere. So that pair of electrons comes back here onto oxygen. And then now this bond will break, and this bond comes over here to form a new carbonyl. So in addition to my epoxide, the other thing that I get is a new benzoic acid, metachlorobenzoic acid, instead of metachloroperoxybenzoic acid. This is the new carbonyl, and this is the new OH. And this oxygen now is on my epoxide. So let's look at how useful this reaction is. If I take an alkene with specific stereochemistry, in this case I have my Z alkene, what I find out when I make my epoxide is that my two methyl groups are syn to one another. So if they're on the same side in the alkene, or Z, they're on the same side in the epoxide product. Likewise, if they're on opposite sides in the alkene, what would you expect to see in the product? They'll be on opposite sides in the product. So an E alkene gives us anti-stereochemistry for our epoxide product. So we can use that reaction in a synthesis here. So if I start with an alkene, and what I want is I want to form an anti-diol. I know how to do that now. Because if you remember, to get anti-stereochemistry, we always would ring open some kind of a three-membered ring. We did it first with epoxides, then we did it with the bromonium ion. So if I open this up with OH minus and H2O, my OH minus has to come in opposite of the leaving group, and that's going to lead to the anti-stereochemistry. So now, using our new reaction that we know of MCPBA, I can take my alkene, form the epoxide, and then ring open that epoxide with hydroxide to get the anti-diol. So this reaction formed the anti-diol. Of course, one of the questions I always ask is what do organic chemists want to do? And the answer is that we want to be able to control everything. So the next question is, how do we get a syn diol? What if I'm starting with that same alkene, and what I really want is a diol with both hydroxides on the same side of the molecule, or a syn diol. And we have a way to do that, and the way to do that is with osmium tetroxide. So we react it with OSO4, and then we're going to reduce the osmium off with sodium bisulfite, NaHSO3, and water. Right, so we have to look at and see how this is going to occur. Well, first we have to know what osmium tetroxide looks like. So osmium has a double bond to oxygen on 4 different places. The shape of it is square planar. So it's a big flat molecule. So what happens is, as it approaches the alkene, both of the oxygens that are approaching have to approach from the same side. So as my electron pair comes out, it will come out to attack one of the oxygens. This electron pair will go into osmium, and this electron pair will come out and grab the other side of the alkene, the place that the electrons left that would have a positive charge. To make an intermediate, and when it makes that intermediate, both of those oxygens, since they're attached to the same osmium as they interact, have to add from the same side. Okay, so my osmium just went from osmium 8 plus back here to osmium 6 plus here. So my osmium is being reduced, which allows my carbons to be oxidized. And then after that, the sodium bisulfite comes around. And what the sodium bisulfite does is it cleaves off the osmium to oxygen bonds. So some of these mechanisms are rather complex for this class, or even not completely understood. So this is an example of one where the sodium bisulfite comes in and cleaves that off, and what it gives us is the antidiol. So you don't have to draw that portion of the mechanism of this problem.